Good morning. Welcome to Shades of Green radio show on KDWN 720 AM in Las Vegas. Our show is produced by Green Alliance of Nevada, sponsored by NV Energy, and I am your host, Stan Hanel. Our producer, Annette Bubak, is also in the studio today. Good morning, Annette.
Good morning, Stan.
How you doing today?
I'm great.
All right. Yeah, Monday. Here we go. Our theme for today's Shades of Green radio show, we're going to talk more clearly to define some of the jargon and terminologies associated with some of the renewable energy, energy efficiency, and electric vehicle industries that we talk about with the guest speakers on our weekly radio show. Every industry kind of has its own special buzzwords and acronyms that might not be familiar to the average listener. So we're going to try and take a little deeper dive into some of these words and the related concept, especially around the area of electricity, which is kind of something that we can't really see. If listeners have questions about today's show, the call-in number at KDWN 720 AM is 702-257-5396. That's 702-257-KDWN. Annette will also be capturing the broadcast on video through Facebook Live. Facebook Live audience, you are welcome to write in and text questions during the broadcast as well. To get started, as customers of an electric utility such as NV Energy, we hear and use a lot of jargon, abbreviated acronyms, and technical terms to describe how electricity reaches our houses through our wall outlet every day. It's always on, always available. We kind of take it for granted, like water. And that's kind of an analogy that they use to kind of describe this flow of electrons that we use to power so many of our devices. Basically, that whole water analogy, there's different terminologies. An electric current is actually like a water current in a way. It's a flow of electrons, usually in one direction or the other through a conductor, through a wire. Basically, it's the actual scientific denotation of it is a quantity of electrons passing a given point. The unit of current is the ampere, or amp we hear, named after Jean-Marie Ampere. He was early scientist in the 1800s who worked on electricity and magnetism. And 1 ampere is 6.28 times 10 to the 18th electrons passing a point in 1 second. So it's a rate of flow as well. A voltage, you can think of it as like when water's sitting in a tub or in a tank, it has gravity pushes down on the water and so that it can flow out through a nozzle or through a valve. That potential or that pressure that comes is called voltage in electricity, and that's kind of what that difference in potential from a more positive battery anode to a battery negative cathode is a difference in voltage. So we have 12-volt batteries. We have in our different devices 1.5-volt batteries, AA's and AAA's, and 9-volt batteries that we use as well. So each of those has a certain amount of potential in order to be able to push that current through a device that's waiting to accept it. And then the devices that use electricity, such as motors and speakers and lights, LEDs, all have certain resistance to that current, and there has to be enough voltage to push enough current to make that device do some kind of work, whether it's lighting up an LED or spinning a motor. And that concept is power. When it can do work, it has a measurement of power, and that's usually called a watt. So we hear the term watt and kilowatts when we get our electricity bill. We also see the term kilowatt-hours, which is power over time. It's how much power we use for how long. And so that kind of is defined as energy. So when we build, there's a meter in your home that's actually reading the amount of current flow through your outlets in the house every day, and then it just kind of accumulates that and counts it, actually adds it all up, and you get a bill for so many kilowatt hours of usage every month. So that's kind of how we get started with that, kind of that analogy. Basically, there's a couple different kinds of currents. Back in the day, a lot of what triggered the need for electricity and the need to send it over long distances was the invention of the light bulb in 1874. And so Thomas Edison partnered with J.P. Morgan and the Vanderbilt family to set up the Edison Electric Light Company, and as a light, he actually also was credited with the invention of the light bulb. In the 1870s, people were able to evacuate a glass tube and put like little platinum and things in there, run electricity through it, and they could get that element, that filament, to glow. And then one inventor just figured he could do it with a piece of carbon, but it wouldn't last very long. It would burn up really quickly. So Edison spent a lot of resources trying all different combinations of filament, and he came up with carbonized bamboo, and that worked really well and lasted a while. So once he had come up with that kind of invention and patented it and pushed it forward, then he needed to be able to light up many lamps at the same time. And so he, with the Morgans and the Vanderbilts, he set up the Edison Electric Company to generate electricity and move it around to different locations. So he was successful. There were a lot of competing companies for a long time, for a while anyway, and then over the 1890s, they kind of either went out of business or they kind of consolidated. So you had about three major companies: Edison Electric, there was Westinghouse, and another one, I think Thomas Jensen, I think, was the third one. So basically, they all were competing to try and make these generation plants. And the neat thing about electricity and magnetism, they are related. A lot of times people understand they're separate phenomenon, but the electricity and magnetism actually interact. If you put electricity through a coil, you get a magnetic field. And if you wave a magnet over an electric coil, you generate electricity. So we'll talk a little bit more about that when we come back.